Next speaker is Michael Cuffaro. Michael Cuffaro is, at the moment, he is an Alexander Humboldt Fellow and connected with the Munich Center for Mathematical Philosophy. But he has a long history at Western. I remember him as a graduate student, one of the most remarkable graduate students we've ever had. He's published deep and interesting papers on Kant, Frege, the philosophy of quantum mechanics, and computability. He has something among the very few people around who had the same range of not just interests but competencies as Bill Dimopoulos. And we're very proud of him as one of our graduates. So it's a very great pleasure to me to welcome Michael Cuffaro. And he's going to talk about methodological realism and quantum mechanics.
Thanks. Thanks, Robert, for that extremely kind introduction, which is probably not deserved. So I want to, how do I click again? Is it, how do I click again? Is it just the?
Click down and point this way, please, Michael.
Oh, I have to point at the computer, that's right, okay. Still doesn't work. It was working earlier though. Where's the on button again? Is it this? Oh, okay. Yeah, there we go. Okay, so I wanted to begin actually to mention another person that passed away very recently, in fact. So Greg Lavers died just a couple of weeks or a few weeks ago in Montreal. And Greg is probably known to quite a few people here, I imagine. He went to school here, did his PhD here. So I studied, before I came to Western to do my PhD under Wayne, I studied for my master's degree with Greg. And so, I mean, I don't have much to say about Greg today because sadly Greg's work didn't really touch on quantum mechanics so much, but I just want to point out that Greg was a brilliant logician and philosopher of mathematics and logic. And yeah, that's it. So I'll just go on. So I want to begin first with a quote from an interview that Mara, I can actually see the screen. So Mara and Rechenberg conducted with Werner Heisenberg in the for the volume that they published on the historical development of quantum theory. It's the third volume of that. And I hope I'm not in anybody's way. I just can't see the screen. So Heisenberg said so in the interview, Heisenberg stated, the fact that xy was not equal to yx was very disagreeable to me. I felt that this was the only point of difficulty in the whole scheme. Otherwise, I would be perfectly happy. What this taught him, he continued, was that if one finds a difficulty in a calculation which is otherwise quite convincing, one should not push the difficulty away. One should rather try to make it the center of the whole thing. So interpretations of quantum mechanics, at least in the way I like to divide up the conceptual landscape, can be thought of as divided into two overall families. So on the one hand, we have those who, like Heisenberg, think of quantum mechanics as a new framework for describing physical quantities. That the lesson of the development of quantum theory in the 1920s was that the puzzles and paradoxes that we were faced with at the turn of the century, classical physics, needed to be resolved in this way with the formulation of a new framework to describe physical quantities. The other main tradition is exemplified by Erwin Schrödinger, and on this conception, the primary lesson of quantum mechanics, the development of quantum mechanics, is that we have discovered that there are wave phenomena that underlie the particle behavior of matter. Now there are a number of subfamilies in both of these groups, and notice that I indicated that they're in both sets of interpretations. There are those who think of quantum mechanics as being complete in some sense, right? And so I put that in quotation marks. Now, the more familiar sense of completeness that one finds in the philosophical literature is the idea that for those who take quantum mechanics to be complete in that sense, that quantum mechanics provides us with, at least in principle, a complete description of physical reality, right? And this is the kind of viewpoint on completeness that is characteristic of Near Everett, for instance. And when it comes to interpretations like these ones, the idea is that they think of quantum mechanics as being incomplete in exactly that sense. In his book on theories, which I'll be coming back to again and again as we go throughout this talk, Bill Dimopoulos wrote, though, that there's a concept of completeness that generalizes the classical concept, and which was shown by Gleason to apply to the quantum theory. This concept does not require that an irreducibly statistical theory, like quantum mechanics, should derive its probability measures from a level of description that corresponds to Einstein's real factual situations. And by real factual situations, to put that in more contemporary language, you can think of like the ontological models framework. And ontological models are a lambda, right? Rather, Bill goes on, completeness in the generalized sense established by Gleason requires that the quantum theory should generate all possible positive real valued measures that are classical probability measures on Boolean subalgebras of the algebra of properties that the theory associates with the physical system. So I'm going to unpack this a bit more as we go along. But my own gloss on this is that, as contrasted with the first sense of completeness that I mentioned, there's another sense of completeness. This is how I would gloss it, is that quantum mechanics provides us with, so to speak, all of the conceptual resources that we need to describe any given, in general probabilistic, physical phenomenon to whatever level of detail that we would like to describe it as. And so I take this sense of completeness to be characteristic of what Bohr thought, of the way Bohr thought that quantum mechanics was complete, and also related approaches. And by related approaches, I include, at least on my reading, so Bruckner, Zeilinger, who I think are very close to what I want to call the neo-Bohrian view. Then there's Chris Fuchs and Britta Schack, Richard Healy, Carlo Rovelli, although perhaps there's a question about whether Adlam and Rovelli really fits into this conception. But in any case, I take these to more or less agree that this is what we should mean by completeness. And the differences between these views, I think, really come down to interpretation of probability and generally how to characterize the conditions under which probability assignments can be made. So for Richard Healy, for instance, there's a physical notion which is given the name of a decoherence context. The decoherence context, which includes the measurement apparatus and also the outside environment, in the same sense that you would get on a kind of an ever-editing view. But that's the sense in which he means a decoherence context. Rovelli talks about an observer system, and in both cases, these are kind of like physical conditions, right? So the existence of some physical frame is what is required in some sense. So then we have Fuchs and Schack, and here it's with respect to a rational agent, and this is a radically subjective conception of probability that goes along with it. So it's not merely subjective in the formal way that you get from an explication, from a formal explication in the way that one is given by Discontinuity. I think here the conception of probability is really the person you need to think about is like Ramsey, right? Ramsey thought that we needed a psychological description of the subject in order to make sense of probability assignments, right? I think that's the kind of idea in the background of Fuchs and Schack here. Now, neo-Bohr, which is the approach to interpretation that I want to focus on today, this is with respect to a so-called Boolean frame. And here, this is objective in a sense that I'll clarify, but it's also epistemic. So the question is what, I'm not going to go into this very much today, but one question one might raise is, so what is the interpretation of probability that really makes sense on a view like this? Now, there is no official view on this. And to be honest, I think I don't recall Jeff Boob ever talking about it. I don't recall any discussion of this in Bill's work. And in my collaboration with Michelle Janssen and Michael Janis, for instance, we didn't go into this too much, but unofficially, I think that the thing that the way that the right way to think of probabilities on this neo-Bohrian conception is the way that Wayne Mervold thinks of probabilities in the context of statistical mechanics. That's unofficial in the sense that it's my personal preferred way of cashing that out. But in any case, Now, the neo-Bohrian view that I'm going to be focusing on is also known as, and I mean, I've started using the label neo-Bohrian with Jeff's approval, but in previous iterations, it's been called the information theoretic interpretation, the informational interpretation, and so on. But fundamentally, it amounts to a defense of Bohr, really, or at least what we take to be essential about Bohr's view, and also an elaboration of how to make sense of what we have learned about the world since Bell in neo-Bohrian terms. Now, that said, the intention isn't per se to make a contribution to the historical scholarship on Bohr, although we sincerely believe that we are given an accurate depiction of this. But we could be wrong, and hence the neo is the way that we qualify this. Now, the view can be traced back to Itamar Petovsky's work. This is his book that Simon Saunders mentioned on quantum probability and quantum logic from 1989. In the 2000s, Petovsky began a collaboration with Jeff Boob, and after Petovsky's death, Jeff became the principal advocate and defender of the view. So he publishing multiple papers on the topic, and these two, well, this semi-popular work on the interpretation of quantum mechanics, or on the approach to quantum mechanics that he advocates, and this fully popular graphic novel on quantum mechanics, which I, with Emerson Doyle, wrote a review on a few years ago. Now, of course, as I mentioned, Bill Dimopoulos, and I'll be coming back to Bill as we go on through the talk. And finally, there's this book that I published a couple of years ago with Michael Janis and Michelle Janssen, and a couple of follow-on papers that we've published in the journal Entropy since then. And this talk will hopefully eventually become this paper that I'm planning to contribute to a volume on how to understand quantum mechanics after 100 years, edited by Johansen and Fay. So I'll begin again, but this time I'll begin with by reading a passage from a letter that Niels Bohr wrote to Paul Dirac in March of 1928, which is shortly after the publication of his Como paper, the famous Como paper, in which he lays out the thesis of complementarity. And Bohr writes to Dirac in reply to a letter that Dirac had sent to him, "I quite appreciate your remarks that in dealing with observations, we always witness through some permanent effects a choice of nature between the different possibilities. However, it appears to me that the permanency of results of measurements is inherent in the very idea of observation. Whether we have to do with marks on a photographic plate or with direct sensations, the possibility of some kind of remembrance is, of course, the necessary condition for making any use of observational results. It appears to me that the permanency of such results is the very essence of the ordinary causal space-time description. This seems to me so clear that I have not made a special point of it in my article." He goes on, "What has been in my mind above all, and I would insert a rather here, was the endeavor to represent the statistical quantum theoretical description as a natural generalization of the ordinary causal description, and to analyze the reasons why such phrases like a choice of nature present themselves in the description of the actual situation. In this respect, it appears to me that the emphasis on the subjective character of the idea of observation is essential. Indeed, I believe that the contrast between this idea and the classical idea of isolated objects is decisive for the limitation which characterizes the use of all classical concepts in the quantum theory. Especially in relation with the transformation theory, the situation may, I think, be described as saying that any such concept can be used unaltered, if only due regard is taken to the unavoidable feature of complementarity." Now notice the emphasis that Bohr lays on the classical idea of isolated objects and the use of all classical concepts. So we might ask, what exactly does Bohr mean by this? So commenting on not this particular passage, but on Bohr's understanding of classical concepts in general, Dimopoulos writes, "By the primacy of classical concepts for understanding of quantum mechanics, I mean," in the sense that he's laying out his own view here, which is a neo-Bohrian one, and I take Bohr to have meant their primacy in the description of experimental results pertinent to the development and confirmation of the theory. In other words, by the primacy of classical concepts, we do not mean a claim this to be a claim about the primacy of classical concepts with respect to the theoretical statements of any possible future physics. Rather, the primacy of classical concepts for Bohr is evidentiary. Malplis goes on, understood as a thesis about the epistemic framework within which physical theories are evaluated, the thesis of the primacy of classical concepts is entirely compatible with the idea that the principles and presuppositions of the classical framework are radically mistaken and incapable of providing an adequate theoretical basis for physics. So Demopolis gives an example. He mentions Stokes' law of fall, which relates the drag force experienced by a particle as it falls through a fluid medium to its density and to the density and viscosity of the medium through which it falls. Demopolis notes that Stokes' law is only valid for small spherical objects that are assumed to produce only negligible effects on the fluid medium. And he comments, nevertheless, he comments on this. The law guided Perens and Thomson's determination of the properties of the molecular and subatomic constituents of matter, even though it was thought unlikely that the relation it expresses could be expected to hold for spherical objects of the dimensions required by the applications of it. Nevertheless, Demopolis goes on, Stokes' law isolates what, in Poincaré's terminology, is a true relation within a limited domain, and I'll come back to this later, between the rate of fall of spherical objects, density, and viscosity that is preserved under a change of application from the continuous media from which it was initially devised to discrete media. It illustrates, Demopolis writes, the fact that the presuppositions of the principles which underlie an evidentiary framework might be false and even known to be false, and the principles themselves have only limited validity without losing their effectiveness for probing the evidence for a theoretical claim or refining the determination of a theoretical parameter. So how does this work exactly? And now I want to move on to another person who's commented recently on the work in philosophy of Bohr, and this is Slobodan Perovic. So the general idea of Bohr's methodology, according to Perovic. So there's a bit more. I think there's a bit more to it than this. In my review of Perovic's book, I pointed this out, but I think that what I'm about to show you here is fundamentally correct. So physical inquiry, I think, for Bohr proceeds in multiple inductive stages, which are associated with different layers of hypotheses of varying levels of generality. So in the first stage, according to Perovic, this involves the formation of concrete hypotheses and models that relate to specific experimental setups whose validity is assumed to be limited to those experimental setups. Whereas in the second stage, this involves the formation of abstract, intermediate, and master level hypotheses that then unify and systematize our understanding of a given experimental domain. So in a bit more detail. So in the first stage, this is characterized by the activity of observing the results of experiments and recording this particular information. It is characterized by the use of so-called everyday language. The idea that pointing out that a spot was registered on this rather than that part of a screen, for instance, which is then made further precise using the mathematical tools of classical physics. And this results, in general, in an experimental account, whereby we describe how we have set up a particular experiment. In other words, what we have done, and what information that yields, what we have learned, to use Bohr's words, about an object that we assume to be able to interact with our experimental apparatus in a particular way, in accordance with whatever lower level hypothesis we formulated with regard to that setup. The second stage, then, aims to unify the experimental accounts that are produced in the first stage. But unlike the first stage, neither everyday language nor its classical mechanical precisifications need directly constrain the second stage. They do indirectly constrain it, insofar as the ultimate aim of the second stage is to have an overall comprehensive grasp of the experimental domain of an area of inquiry in general. At least this is true until new experiments are performed. And this is probably the most important part. For despite the fact that an accepted master hypothesis will be implicit in any account of a given set of data, the first stage of the inductive process can in principle continue to operate effectively independently of the second stage, as long as the novel theoretical relations that are formulated in the second stage don't directly manifest themselves via controllable parameters in the lower level experimental accounts, right? And that's exactly the case in quantum mechanics. Coming back now to the classical concepts. So I'll read from another letter, this time to Schrödinger, from October 35. And here Bohr writes that by emphasis of the point that the classical description of experiments is unavoidable amounts merely to the seemingly obvious fact that a description of any measurement arrangement must, in an essential manner, involve the arrangement of the instruments in space and their function in time, if we shall be able to state anything at all about the phenomena, which is sort of what I just said, so just to confirm that. Now, but there's a somewhat more subtle point here, which Dimopoulos brings out, is that Bohr appears to be claiming that this is something that any description of measuring instruments must include in order to play the epistemic role that they do. So what is classicality according to Dimopoulos? So on Dimopoulos' account of classicality, the central characteristic of a framework or theory whose concepts are classical is the commutativity of the algebra of physical concepts, the parameters, physical magnitudes, and dynamical variables with which it characterizes physical systems. So in this sense, and it was brought out a little bit in the last talk, and one of the questions, I think. So equivalently, classicality consists of the Boolean character of the algebra of all of the properties and propositions that are associated with each physical system. And so what I meant is this last point. So on this view, classicality is a characteristic that attaches to the interrelations of the physical concepts of the theory, rather than to the concepts themselves. Okay, so I'm not going to read it again, but for the rest of his talk, I'm essentially going to be framing the rest of the talk around this large quote that I read at the beginning. And so all of these highlighted passages will have a corresponding heading as we go forward. So let's begin by asking the question, what are observational results? What do we mean by observational results in this context? So as an example, I want to point out that Newton's phenomena, the phenomena that Newton appealed to in his argument for universal gravity, are phenomena in the sense that is relevant to my talk today. And I'll just read the first one and let you read the rest. But number one, this is a phenomenon. The circumjovial planets, by radii drawn to the center of Jupiter, describe areas proportional to the times, and their periodic times, the fixed stars being at rest, are as the 3/2 powers of the distances from the center, and so on and so forth. But the upshot here is that physical phenomena can be mathematized. So the idea that you shouldn't be thinking of as like some kind of like psychological account of a sense impression, and so, like physical phenomena can be mathematized, and there's a particular way that they must be mathematized in order to count as observations, you might say. And in fact, what I just said is kind of the idea that George Boole uses in his account of what he calls the conditions of possible experience with respect to our observation of statistical data. So George Boole writes of these conditions of possible experience such that when satisfied, he writes, they indicate that the data may have, and when not satisfied, they indicate that the data cannot have resulted from an actual observation. So he explicates this in the following way. So suppose we have a set of rational numbers p1 through pn representing the relative frequencies of n logically connected events. So imagine it will rain in London today is E1. It will rain in Montreal today is E2. And E3, let's say, it will rain both in Montreal and in London today. These are three logically connected events. And we then ask, what are the necessary and sufficient conditions under which the PEI can be realized as probabilities corresponding to the logically connected EI in some probability space? And Potofsky gives a general algorithm. Given the logically connected events, E1 through En, we write down a corresponding propositional truth table. We then associate rows of the truth table with vectors of extreme probabilities. And then we take the convex hull of these vectors to yield a polytope. So in general, it's going to be a high dimensional polytope. But in the case of 3, for instance, you'll get an easily visualizable one like that. We then take the convex hull of these vectors to yield a polytope, and we determine the linear inequalities that are associated with each of its facets. As Potofsky showed, a special case of this is the Bell inequalities. And so it's interesting in the sense that the statisticians of the 19th century kind of anticipated Bell's result, although they weren't thinking about physics, right? So because this is the kind of thing that people were talking about in the 19th century, as Stofsky himself points out. And in the book that I published a couple of years ago with Janis and Janssen, we showed that we considered another context. And this is the context which is associated with a thought experiment of David Merman, where you have three random variables, three true-valued random variables, which are constrained to have one of three particular measurement settings. And we asked the question of, what are the constraints on the possible correlations between these three variables? And I won't go into the details too much, well, a little bit, but not too much. But what we showed, or rather what Michael Janis showed, is that we can express the constraints on the correlations in terms of the following, call it the elliptope inequality, because the result then geometrically is this inflated tetrahedron, or what we call an elliptope, which relates the correlations among the random variables given in terms of the Pearson correlation coefficient, which I define here, in terms of the standard deviation and expectation value. Okay, so coming back to this figure. So this is a general constraint on the correlations between three random variables, regardless of what one's underlying conception of the system one is talking about is, right? As we showed, the derivation of this inequality relies on the fact that we can express this linear combination of the three random variables in this way. Now, as we argued, modeling that relation in a locals and variables theory requires a joint probability distribution, or the values of x, y, and z, for that to make sense. And what that means is that in the case of two values per ticket, or two values per random variable, our random variables are called tickets here in our parlance. Although the elliptope constrains the correlations, it doesn't tightly constrain. So the possible correlations in that case collapse to just the regular classical tetrahedron. No surprise. You can approach the elliptope if you increase the number of values per ticket. So at 3 values per ticket, you have this polytope. And then as you increase the number of values per variable, these are actually projections on a very high dimensional polytope, which abstracts away from things that don't actually make sense. But the result is that you have a visualizable space of possible correlations. And as you increase the number of values per variable, you get closer and closer to the elliptope. There's a subtlety depending on whether you have an odd number of values or an odd number of values, which is this case, or an even number of values, which is this case. So it's only in the case where you have an odd number of values that you can really have a hope of really covering the whole thing. Because in the even case, you have this cutoff portion here. But the point is that you can approximate that as you increase the number of values per variable. In the case of quantum mechanics, however, you get full saturation of the elliptope for all values of spin, including the spin half case, which corresponds to the 2 values per variable case. And the reason, as we argue, is that in quantum mechanics, one can assign a value to a sum without assigning values to the summands. Now, the idea that you can assign a value to a sum without assigning values to the summand is something that isn't possible in classical theory. And the reason is that the kinematical constraints of quantum mechanics are less restrictive than the kinematical constraints of classical mechanics. And by this, I mean kinematical constraints in a broad sense that is originally due to Michel Janssen in this nice 2009 paper. And by this, I mean the constraints imposed by theoretical framework like quantum mechanics on our physical description of a system independently of the specifics of its dynamics. Not independently of dynamics as such, but independently of the specifics of its dynamics. The kinematics of quantum mechanics are, as I said, less restrictive. So you can consider, for example, the operator S hat, which we form by taking a linear combination of 3 other operators. And there's no requirement that each operator must be assigned, each observable must be assigned a value if you assign a value to the observable corresponding to the linear combination of them. That's not the case in quantum mechanics. And so that, in a sense, is what is meant when people who defend the informational interpretation or near-Bohr interpretation mean when they say that quantum mechanics is all about probabilities. This isn't an ontological claim, right? It's a slogan in the sense that it's a claim about where the novelty of quantum mechanics is located. And the novelty of quantum mechanics is that the kinematical constraints are, as I said, less restrictive. It's not about some stuff some like abstract stuff that's called probabilities that comprise of the ontology of the on this view. So the slogan also conveys the idea that quantum mechanics is a framework that can in principle be applied to any type of physical system. Now, understanding why quantum mechanics, but not classical mechanics, allows us to saturate the ellipto for all values of spin, that's only one example of a problem that can be solved by appealing exclusively to quantum mechanics kinematical constraints. So some further examples, and these are described by us, but in particular by Michel in this part of our book. And I won't go into this in too much detail now, but I'll just list these off. So one example is the accounting for the particle term in Einstein's 1909 formula for energy fluctuations in blackbody radiation, accounting for the formula for the electric susceptibility of diatomic gases, accounting for why electron orbits seem to depend on which coordinates you choose to impose a quantization condition. And as I mentioned, this is another example of a problem that can be solved solely by appealing to quantum mechanics kinematical constraints. Now let's go in a little bit more detail about this. So in classical mechanics, as contrasted with quantum mechanics, so specifying a system state yields an answer to every yes or no question that can be asked about a particular observable quantity. For example, is the value of the observable, let's say A, within the range delta? In that sense, the classical state is a truth maker. And by that, I just mean a logical sense, not in the sense that might be familiar from metaphysical context. In other words, it's a truth maker in the sense that it determines the answer to every yes or no question that one might ask about the quantity, irrespective of how we interact with the system. And that's simultaneously true for all observables. The state determines the answers to all questions concerning all observables in advance. In quantum mechanics, states fail to be truth makers in two different senses. And these are, originally Potofsky referred to these as a big measurement problem and a small measurement problem, but really they're two different aspects of the regular measurement problem that we're all familiar with. So the big problem is that specifying the state psi yields in general only the probability that the answer to a given experimental question will take on a given value. Now, that's not as much of a departure from classicality as one might think, in the sense that conditional on the selection of a given observable, the observed states will be describable by a classical probability distribution. The small aspect is such that the classical probability distributions that you can associate with individual observables can't be embedded into one global classical probability distribution over all observables. So in quantum mechanics, we can only say that conditional upon inquiring about the observable A, there's a particular probability distribution that one can use to characterize the possible answers to that question. Moreover, quantum mechanics' unitary description of a measurement interaction doesn't by itself prefer any one of these. This is also known in the context of the Everett interpretation as a preferred basis problem. It's really the same problem, just thought of in a different way. Now, slightly more formally, in classical mechanics, we have it that an observable A is represented by a function, f of A, that acts on the phase space of a system. Whereas in quantum mechanics, and this is exactly parallel, an observable A is represented by an operator, A hat, which is also defined to be acting on the Hilbert space of the system. Now, in classical mechanics, with f of A, we can associate a Boolean algebra, curly A of yes or no questions concerning A. And likewise, in quantum mechanics, with the operator A hat, we can associate a Boolean algebra, curly A of yes or no questions concerning A. Now, as I mentioned before, in classical mechanics, points in phase space can be thought of as truth makers, in the sense that fixing omega, the state omega, fixes the values for every observable. And moreover, the Boolean algebras corresponding to the individual observables can be embedded into one global Boolean algebra. In the case of quantum mechanics, vectors in Hilbert space are not truth makers in that sense. So fixing psi only fixes conditional probabilities for the outcome of experiments given that you measure a particular observable. Moreover, well, and it's just another way of stating that point, the Boolean algebras, curly A, curly B, and so on, are not embeddable into one global Boolean algebra. Now, Dimopoulos, in commenting on this, writes, the shift in the algebraic structure of observables and properties which marks the transition from classical and quantum mechanics is a radical departure, even by the standards set by the transition from Newtonian ideas that characterize the special and general theories of relativity. In the case of quantum mechanics, each observable is represented by a Boolean algebra of possible properties corresponding to the possible values of the observable, and this is reflected in the Boolean algebra of possible effects that are elicited by measurement interactions involving the determination of the value of the observable. He continues a little later on, and the rest of the talk I want to try and convince you of this. The radical disparity between the algebraic structure of the classical and quantum mechanical frameworks is not a problem that must be overcome, but is rather the true basis for the uniqueness of quantum mechanics. In the evolution of the physical theories that Bohr sought to highlight by his insistence on the methodological primacy of classical concepts. Okay, so in order to convince you of this, I want to begin by discussing what I want to, essentially the received view, right? Or what I'm calling here the traditional metaphysical picture, as a kind of contrast to the kind of view that I want, the kind of approach that I wanted to defend in the end. So on the traditional metaphysical picture, so I call it traditional, but I think it's traditional in the context of philosophy of physics. Outside of philosophy of physics, I mean, maybe it's less of a received view, but in the philosophy of physics, I think this amounts to a kind of received view. And it's the idea that dynamical variables like position, momentum, the direction of a particle's spin, and so on, should be understood as being the manifestations of an underlying reality whose properties are such as to give rise to the values of the observable quantities that are revealed in our experiments with systems. So this is what John Bell means, for instance, when he writes, and this is his emphasis, observables are made out of beables. Now, since in quantum mechanics, the values of observable quantities can't in general be consistently interpreted because of the big and small measurement problems, as representing the antecedently given properties of a physical system, in other words, since there's no Boolean algebra of properties that we can assign to all of a system's observables, there are essentially two options. The first is the hidden variables program. And this is to posit further physical quantities over and above what's described by quantum mechanics. That can be so interpreted. And the second alternative is to basically the Everettian approach, which is to argue that, at least in principle, all of the approximately classical physical possibilities that are described by a given state vector are realized in some sense. And in some sense, that's just a placeholder for your version of Everettianism. Now, the point of this talk is not to criticize other approaches. The point of the talk is to clarify what I take to be the view that I want to defend. My own view is that I don't have any objections. Not that I don't have any objections, but I don't want to criticize the idea that these can work. Unless I'm given a demonstration that one of these approaches cannot work, I assume that they do work. And so the point of my talk is not to criticize other approaches. The point of my talk is to clarify the approach that I want to defend. And so I want to clarify it and give you what I take to be the motivation for it. So on the Neo-Bohrian approach, the important thing to point out is that it isn't per se opposed to the traditional metaphysical picture, right? Because that picture would be apt in the sense that one might be led towards that picture if one thought that at least a textbook or some textbook classical mechanics were fundamental. At least arguably so. I think that even in this case, there are arguments that one might use to push against that. But nevertheless, the point is that we're also open to the possibility that it's not apt. So it's not. We don't take that position as a dogmatic position. We're open to it perhaps being false. And the point for an approach like the one I want to defend is that how we carve nature at the joints is something that we should motivate by physical theory. not what we should get for free from physical theory, but that it should be motivated by physical theory, and rather than motivated dogmatically and a priori. Now, it's important to point out that the approach is instrumentalist in the sense that ultimately the goal of even a so-called fundamental physical theory is to represent phenomena, not necessarily the so-called reality that underlies the phenomena in a systematic way. So physical theory in that sense is a tool, right? So if that's what one means by instrumentalism, then fine, we're happy to accept that label. However, instrumentalism in that sense is, I want to argue, compatible with realism on a more reasonable methodological instrument of what it means to be a realist. So the important question here is not whether, but how to assign physical properties to what one takes to be the system of interest that is responsible for a given phenomena. So this amounts to the demand, and this, I mean, in some sense, I take like people like Fuchs and Schacks to kind of deny this, right? So like this is a substantive claim. This is a substantive position here. It's not just a wishy-washy thing. It amounts to the demand that we be able to meaningfully account to one another how we have set up a particular experiment. In other words, what we have done in Bohr's terminology, and what information it yields in Bohr's terminology, what we have learned about an object that we model is able to interact with our experimental apparatus in a particular way, something I kind of went over before. So that, we take it, is a methodology that's characteristic of what Bohr called the ordinary causal description, a phenomena that a framework like classical mechanics makes precise, and for which quantum mechanics provides a generalization. And providing an ordinary causal description of phenomena functions as a fundamental constraint in that sense. Now, Howard Stein famously, famously to some in any case, argued that the principal difficulty in making sense of the connection between the observational and theoretical parts of a physical theory isn't the problem of trying to get rid of the theory latence of observation. It's the reverse, right? It's like the problem is to how can we account theoretically for observation? He writes, it would be impossible to understand a theory as anything but a purely mathematical structure. Impossible, that is, to understand a theory as a theory of physics if we had no systematic way to put the theory into connection with observation or experience. He writes that the relation between observation and theory is not deductive. So he writes, there's no department of fundamental physics in which it's possible in a strict sense to deduce observations from data and theory. And he suggests that the only way to connect theory and observation is by schematizing the observer within the theory. And he means this in a way that goes beyond the formalism that one used to describe a system, right? So Stein himself doesn't elaborate too much on that. He makes those remarks in the 94 paper that I mentioned. Some reflections. But Eric Curiel more recently has elaborated on this a little bit more, and I think what he says here is very helpful. So Curiel writes that, elaborating and explicating this a little bit more, we need a way to understand the substantive, physically significant contact, the epistemic continuity, as it were, between a precisely characterizable situation in the world of experience and the mathematical structures of what we usually think of as our theories. Such understanding should at a minimum consist of an articulation of the joints where meaningful connections can be made between the two, and would thus ground the possibility of the epistemic warrant we think we construct for our theories from such contact and connection. He continues, I mean something like, in a model of an experiment, to provide a representation of something like a measuring apparatus, even if only of the simplest and most abstract form, that allows us to interpret the model as a model of an experiment or observation. He continues, one cannot even define physical quantities. For example, temperature, without explicit schematic representation of the observer, much less have understanding of how to employ the representations in scientific reasoning in ways that respect the regime of applicability. Now, what I want to point out here is that this was well understood by Bohr. So commenting in the context of his discussion of Heisenberg's microscope experiment on the use of the superposition principle to explain particle-like quantum phenomena in terms of the concept of a quote-unquote wave packet, Bohr writes, indeed, a discontinuous change of energy and momentum during observation cannot prevent us from ascribing accurate values to the spacetime coordinates, as well as to the momentum energy components before and after the process. The reciprocal uncertainty, which always affects the values of these quantities, as will be clear from the preceding analysis, is essentially an outcome of the limited accuracy with which changes in energy and momentum can be defined when the wave fields used for the determination of the space-time coordinates of the particle are sufficiently small. So the upshot is that on a neo-Bohrian approach, quantum mechanics is understood as elevating the idea, which Stein and Curiel have argued for on the grounds of practical and epistemic necessity in the case of classical theory, that it is required to schematize the observer in relation to the theoretical description of a system in order to understand a theory as a theory of physics at all, to the level of a postulate. Bohr was actually quite explicit about this. So this is from 58. In the treatment of atomic problems, he writes, actual calculations are most conveniently carried out with the help of a Schrödinger state function, from which the statistical laws governing observations obtainable under specified conditions can be deduced by definite mathematical operations. It must be recognized, however, that we are here dealing with a purely symbolic procedure, the unambiguous physical interpretation of which, in the last resort, requires a reference to a complete experimental arrangement. Disregard of this point has sometimes led to confusion, and in particular the use of phrases like disturbance of phenomena by observation or creation of physical attributes by objects by measurement, something kind of language like Chris Fuchs actually uses quite a bit, is hardly compatible, Bohr writes, with common language and practical definition. So on a neo-Bohrian approach, an observer should be thought of, or rather an observational context, is represented as a Boolean frame. So the Boolean, which is, in other words, a Boolean algebra within which one represents the possible yes or no questions concerning a given observable A that can be asked about the system of interest. Questions of the form, like I mentioned before, is the value of A within the range delta. Given the schematic representation to the relevant scale and for the relevant purposes of an observer in that sense, one may then use the language of quantum mechanics to give a physical analysis of how the observed relative frequencies of outcomes of assessments of the measurement device, assuming that's ideal, and if it's not, we can move back to Heisenberg cut, describable using a particular classical probability distribution that can be thought of as determined in conformity with the dynamics of the system in interaction with the device. So to sum up, in classical mechanics, as a matter of logic, the state is a truth maker in the sense that one can always argue, putting Curiel and Stein's arguments to the side for the moment, that including the representation of the observer, of the observational context in one's analysis of a system's dynamics is superfluous, at least in principle. But that's not the case in quantum mechanics, where the introduction of Boolean frame is required, according to Bohr, to interpret the outcome of a measurement interaction as providing us with information about the system of interest. Just the basic idea. Okay. So what exactly then is exhibited by the state description on a neo-Bohrian view? It's not per se a collection of antecedently given properties that are possessed by a system. Rather, what's exhibited is the way I want to gloss it, the structure and interdependencies among the possible ways that one can effectively characterize a system in the context of a physical interaction with it. Now, indeed, that, at least I would argue, is no less true of a classical state description. But because the probability distributions over the values of every classical observable are determined independently of whether a physical interaction through which one can assess them is actually made, there's an invitation to think of them as originating the properties of an underlying physical system that exists in a particular way. But the more complex structure of observables related by quantum mechanics does not similarly invite the inference from the values of observable quantities to the properties of an underlying system in that sense. That said, in a given measurement context, which we can by assumption effectively describe in Boolean terms, one can give a dynamical model of the system for that context also in such terms. It won't suffer from the small measurement problem because the observables in that context will all commute, but it will suffer from the big measurement problem. However, in any given measurement context, if you really want to give a deterministic story, you can give one limited to that context, because it will always be possible to effectively interpret the indeterminacy of measurement results as stemming from our inability to precisely specify some relevant physical parameter in whatever dynamical model we use to conceptualize that experimental context. So this comes back to the idea that I mentioned before of like the first stage of the inductive process. This is what we're describing here. Moreover, the probability distributions that one can assign in those measurement contexts are quantitatively related to one another in a specific way, which are subject to the constraints imposed by the kinematical framework of quantum mechanics. Now, you might ask whether anything can really be said, or whether anything can be, you might ask whether nothing can really be said about what the world is like independently of observation on this view. And you might worry that nothing can be said, but on the contrary, I would respond. In fact, non-dynamical quantities, such as quantities like mass, spin, charge, and so on, assignments of values to those quantities will be valid regardless of the experimental context. As for dynamical quantities, what we can say is that the world is such that all of the effectively classical pictures, effectively Boolean pictures, that one can draw of it under the precisely specified experimental conditions corresponding to each of them are precisely relatable to one another in the way described by quantum mechanics. And that's not a trivial thing. Now, the question might arise of whether that statement that I made in B depends physically or metaphysically on the existence of conscious observers. And what I want to say is, no, or anyway, that's not the point, right? So in some sense, yes, observers need to exist in order to do physics. But nothing has changed, at least on our conception of what classical theory was like, in the metaphysics of the observer. Physics is something that we do, right? It's not a rock that we find in the ground, right? Physics is something that we do. And so there's no difference in the metaphysics of observers between classical and quantum mechanics in our view. And because that's not really the point of the innovation of quantum mechanics. Right? The point, rather, is that a schematic representation of what relevantly constitutes an observer, in other words, a classical conditional probability distribution, or in other words, a Boolean frame, is being used as a formal tool with which to describe how the various dynamical possibilities that are implicit in the world are necessarily related to one another. So physics is in the business of describing the true empirical relations that obtain in the world. And here's a visualization of some of these, right? So we have like Bell inequality constraints and Tiralton-bound constraints and so on. Of course, that doesn't amount to the description of a substance existing in itself in the traditional metaphysical sense. But on the empiricist perspective, embraced by the neo-Bohrian interpreter, we were never committed to this. Now, I've gone to some pains to emphasize that we shouldn't think of these true empirical relations as somehow comprising a substance. But now I want to possibly confuse you a little by maybe suggesting that maybe there is something like this going on. But that's not what I mean. So I'll try to be as careful as I can. So I think that there's an analogy here that we can draw between this kind of exception of what we think we are discovering when we do quantum physics and how we can characterize what Helmholtz was doing in the 19th century in his pursuit of, well, put it in one way, knowledge of physical geometry. So Helmholtz showed how Euclid's first four postulates presuppose the principle of the free mobility of rigid bodies. But postulate 5, the parallel postulate, describes a global feature of space, which doesn't likewise follow in the same way for the principle of free mobility. He then showed how iterating a number of basic local constructions can result in a series of sense impressions through which one can become acquainted with the global structure of the space. Now, his analysis of how that is done actually highlights the role played by the conditions for the possibility of measurement, which are made precise through the concept of a rigid body as the basis for the pre-relativistic belief that the global geometry of space is Euclidean in the first place. So quantum mechanics similarly allows, this is the analogy I want to draw, it similarly allows a piecing together of the Boolean algebras that characterize individual observables associated with a system so that the resulting global structure of the system's abstract space is non-Boolean. But it's a very similar idea that's going on, I think. Right? It's the idea that local construction doesn't determine the global result, right? And that these global posits really have to come from outside, in a sense, if you want to take the postulate 5 to be a priori, right? It really has to be imposed. Otherwise, if it's not imposed, then you can work out a kind of procedure in the way that Helmholtz did. Now, I'll end just with a few words, just giving you a nutshell view of what I'm calling the Neo-Bohrian view. So quantum mechanics, in the sense of what it objectively describes, is about probabilities. These are understood to be, to use von Neumann's phrase from 27, given from the start. In other words, as objectively or non-contextually associated with a given concrete measurement context. And so here I want to compare. I think there are some similarities here with Myhrvold's concept of epistemic chance. Quantum mechanics describes the relations between these in general non-Boolean way, which amounts to saying that the various probability distributions that we can use to effectively characterize a phenomena associated with commuting sets of observables can be embedded consistently into a global probability distribution over the simultaneous values of all of them. But despite that, it provides, in any given measurement context, a recipe through which one can acquire information concerning the system through interactions with objects whose relevant parameters can be effectively described using classically Boolean means. We can think of them as being on or off with a certain probability, which is determined by the dynamical properties of the system according to the dynamical model that one constructs of it for that context. You can even make up fantastic ones, like raffle tickets in the way that we did in the book that we published a couple years ago. So in other words, quantum mechanics allows us to do physics in much the same way as we always have. But it doesn't follow from any of that nature needs to be such as to allow, at least not in a natural way anyway, for a globally Boolean description of all aspects of all dynamical phenomena that physics is concerned to describe. And with that, I'll end. Thanks.
Thank you.
I thought several would have their hands up.
Use that. Use that.
Yes, so that was a wonderful talk, and I enjoyed it so much I found myself agreeing with almost every single word you said, and yet fundamentally disagree, because all of the words that you didn't say. So so really, it's a wonderful presentation which fits very much with especially my more recent views as to the issues of probability, in particular contextuality, and so forth, in an instant. And what I found absent, and the words that you didn't say, were all relating to dynamics. So, that's a sort of the overall reaction, as it were. And can I just be a bit more specific and pose it to you as a specific challenge, that consider what Bohr had to say about the observer. You present him, and it's very neo-Bohrian, with the emphasis on neo, because, as it were, you've got quantum mechanics and you don't have a classical domain. And then it's up to us to choose the Boolean frame, as it were, and that's going to represent the observer and so on and so forth. Whereas Bohr did it sort of the other way around, didn't he? He started off with a classical background, and the Boolean frame was really introduced to give us the quantum reality. And I think it was the exact opposite sort of approach that Bohr used in that respect. But just on the very specific point that this issue of focus on the observer is not needed, except in quantum theory, because it's rather important to your general theme that quantum theory does involve something genuinely unique that was absent in classical theory, and you're positioning this issue of the observer in that. I put it to you that in order to model the motion of the Earth around the sun and to account for the phenomena, it was rather essential that the observer was situated on the planet Earth. It was very essential to Galileo in countering arguments that if the Earth was in motion, there would be a giant wind and objects would fall, behind us in the direction of travel and so on and so forth. That no, the principle of inertia, the atmosphere is carried along with the Earth and the observer with it, and therefore one understands and analyzes what that observer will perceive. So this principle, I would suggest, has always been present in physics, has always been fundamental, and is always bound up with the dynamics above all. And the particular way in which I know Everett would be turning in his grave, if only he had a grave, is because he modeled the observer in this abstract way, precisely as you are doing, in quantum mechanics, and then it was the unitary dynamics that dictated the branching structure. Yeah. So it's the combination of modeling the observer plus the dynamics that tells you what follows and what can be observed and so forth. So
So with respect to the first point, so I don't agree. I mean, so as I mentioned on one of the very first slides, for Bohr, quantum mechanics is a generalization of. So I don't agree that we disagree actually, because for Bohr, quantum mechanics is, as I mentioned, a natural generalization of classical mechanics. So yes, there are classical ideas that are being imposed, but because we need to make sense of how we can learn about quantum mechanics, and so it's not a part of the theory. And so the idea that we can model the observer in the way that we do in Everett is a non-starter for Bohr. So we model the observer outside of the theory. Of course, we can always move back the cut and include what we took in that situation with the observer to be a system. But the observer qua observer always must stay out of the quantum description on Bohr's view, because we need to be able to make sense of how we can learn about the quantum system. And we can learn about the quantum systems using apparatuses that we can conceptualize classically, and that's Bohr's point. So there is, in a sense, a divide in our description of a system between the classical part of that description and the quantum part of that description, which in principle can be movable, and which further implies another measurement, but I don't take it to be the case that we actually disagree about what Bohr what the direction in which Bohr approached the question. So I just want to point that out. So with respect to the point, what's new in quantum mechanics is not the introduction of the observer, right? Because as I attempted to point out here, so it's not that we don't care about the existence of an observer, but it's that it's not the point. And what I mean by it's not the point is that I agree, and the observer was important in classical theory, and nothing changes in quantum theory. Is the point that I'm trying to make. What changes is the way that we characterize the observer in quantum theory. Whereas in classical theory, we allow that in principle we can describe everything using one systematic description that pertains to an object conceived of as a system. In quantum mechanics, we posit that we cannot do that, in a sense, right? That's the point of it as a postulate. The schematic representation of an observer in the neo-Bohrian sense, unlike in the Everettian sense, is not an observer in the sense that you have a God's eye view on it. There's always an observer in the Bohrian sense. There's always an observer, regardless of whether you move back the cut to describe what used to be the observer in that former context as a system in the latter context. And so that's what I take to be a fundamental difference between Everett and Bohr.
Yeah, I mean, if I can just interject, all of your words in your talk I completely agreed with, and it was only the ones that were missing. Now you've applied new words, and I disagree with almost every one of them.
Yeah, no, but it doesn't surprise me that we disagree about that, because that's what I take to be the fundamental difference between Everett and Bohr.
We'll talk more.
Yeah.
Wait, can you take that little microphone, Carla?
Well, I love this. I think I've subscribed everything you said. I would like to be able to give a talk like that and say the same things.
Thank you.
I want to make a point. Actually, I want to say something about what you said about the connection with the relation of quantum mechanics. It's true that there is a difference, the one you pointed out. But what it's happening in my mind, at least, and in fact,
We'll get to it.
I'm right. Yeah. It doesn't matter. At the beginning, you have a slide in which you made that point. Is that I got some criticism strong about a relation of quantum mechanics, specifically from Andrea Di Biagio, with whom I'm ending up writing a paper. And the criticism was, come on, it's not just a system with respect to which you assign values to other systems, blah, blah, blah. It should be less, and it should be a commutative algebra of observable self-observing system. Otherwise, it doesn't work for technical reasons because if a system A and system B, it can be that the system B has information about A in different manners. Different subalgebra of B have informations about A. So which variable of A has value with respect to B? Ones or the others? Okay, which forces me to backtrack and to say the A observables take value with respect to B. No, with respect to an abelian subalgebra of B is observable, which brings extremely close to what you're saying. At this point, the difference is in emphasis. It's not just a abelian algebra, a Boolean, but it's an abelian algebra of the physical system, which is the observer, which could be you and I, or all the Earth in our liquid Earth domain, or whatever. So from this perspective, I think the way, and this is I'm writing this paper with Andrea, trying to somehow. So we're backtracking toward you very much in that. This perspective, maybe the difference that remains is only an emphasis of what is this epistemic domain. Is that do we really want to view it sort of abstractly, or I would like to view it much more concretely? I mean, I make an experiment in a laboratory, and I am a piece of the world. I am a system, but I am more than a system, because what I'm describing myself, it's a billion subalgebra of the full algebra you could measure on me. And with respect to me as a system and as a billion subalgebra of the algebra that describe me, there is a description of something else. And what I think relational quantum mechanics add to us is the possibility of, which is explicit, which I don't think you would disagree, of viewing the perspectival, the subjective perspective coherently from the outside as simply a correlation between some variables and other variables. So I know, if I don't think of me observer, but the apparatus as observer, I know exactly what it means that the apparatus has information about the measured thing. It means that me as an observer, if I measure the apparatus, I can predict then what I'm going to see as the... So this doesn't allow me to get out from this perspectival thing. Like you, I don't want, and unlikely our common friend, we don't want the God-eyes view on that, because I don't think it's useful. You think it's useful. But the emphasis, I put it much more on the fact that the observer itself is a fully quantum system, normal, like anybody else, that can be described from the outside. Of course, in the moment in which, and that was very important at the beginning, you said you want memory, you want persistence, then you start adding properties to what you want to call an observer. But then it's an issue of names. We want to call an observer guy with a mind, or also without PhD, or just an apparatus, or just an ant, or just a sun. But that's what we want to call observer is completely relevant for understanding quantum mechanics.
Yeah, I mean, I think I have a somewhat richer notion of observer than you. The observer must be able to play the epistemic role. Like the observer must be capable of reading the measurement instrument, right? Of whatever instrument is being used to interact with the system, in the sense that.
Yeah, sorry to interrupt you, but that's an issue of name. How do we want to use a name? The question is what to make sense of the theory, the transition amplitude, the physical, all the mathematical part. What we can drop and still use and still make sense of what. That's probably, maybe we don't. Maybe I want to drop it more than you, something like that. What you're saying?
Perhaps, but
we both want to drop consciousness of the.
Yes.
We both want to drop necessarily language, blah blah, but you want to keep more. Is that what you're saying?
Well, I mean, so like, what I want to drop is any talk of like somehow observers, big O, being special in quantum mechanics, which I don't think they are. But when I say special, I mean as compared with classical mechanics, right? I don't think there's a difference in the metaphysical conception of observer between the two. I don't think so, and that's kind of the point of the slide I put up earlier. So to maybe approach the point that you're getting at, because I don't think we really fundamentally disagree, but maybe let me just tell you the way I think about it, and then maybe we can see like to the extent which we do or do not disagree. So my own view is pretty close to what I think of as Bohr's view. So Bohr and Heisenberg had a disagreement, right? About, well, an initial disagreement in any case, about the movability of the cut, right? So Heisenberg thought that the cut was freely movable, and Bohr seemed to insist a bit more on the rigidity of the cut. But I don't think there was a real disagreement of substance between them, right? Or Heisenberg was emphasizing the abstract nature of the cut and the fact that it's an epistemic cut. Whereas Bohr, although he didn't disagree with that, he wanted to emphasize that although the cut is epistemic, it's nevertheless associated with a concrete physical context, right? So I think what you want to emphasize is the concrete physical context.
Right.
And what I want to emphasize is the epistemic layer, or what you want to call it, that one requires in order to interpret that physical context.
Yeah.
And I think it becomes a bit difficult without that epistemic step to make sense of how probability assignments are made, of how we could characterize a system in the context of some observation, given the preferred basis problem, essentially, right? Given what I call the small measurement problem, because there's always a choice of which observables we want to consider as being coupled with a system in which we don't, right? There's a movability of the cut.
That's where I backtracked. That's what I said. An observer is not a system. It's a given commutative sum algebra of the system.
So in that sense, we do agree. Yeah. We do.
Yeah. I'd love to continue this conversation.
Thank you.
Okay, well, thanks very much, Michael. Break for lunch.